let's begin. So just let's go about a little bit of the content that we are going to be looking today. We're going to talk about the urban cycle, why it is important, why we should care about it, what are the tools that we need to analyze it and model it, and a couple of intermissions just to give you a brief history about some of my work. And after that, I will talk a little bit about the OpenWaterAnalytics Initiative, OWA. So regarding my background, there are two sides to this coin. So on one side, I'm a civil engineer with a background in hydroinformatics and sanitation and an unfinished PhD. I started working with development with Python around 2009, and since then I've been part of the core developer team of Spider IDE and the PyB project since last year. So on the other side, I'm working as a software engineer for Anaconda Inc. Maybe you have heard of Conda and the Anaconda distribution. But the reason I'm giving this talk today is because I'm trying to go back to the point where my two passions intersect. On one side, water modeling and hydraulic modeling with development. And this is why PySWMM is going to be discussed today. So we are more or less familiar with the water cycle since our high school days. There are different processes, different flows of water from evaporation, condensation, rivers, runoff, infiltration into the ground, percolation in the ground layers. The urban water cycle, on the other hand, is pretty much the same, except there is human intervention. We have dams, crops, pipes, roads, and we're putting a lot of poop into the water. So how do we go about understanding this system? How do we model this system? How can we get some insight on how it works? How can we control what happens? How we build our structures? So the first thing we need to understand is what's the purpose of a model? What is a model? So it's any tool that we use to better understand, visualize, or simplify reality so that we can try to better comprehend it and analyze it. So models can be pretty simple, or they can be pretty complex, depending on your needs, depending on what you need to model, depending on what you need to do. Also, the picture there by René Magritte, it's the thing that says there is, this is not a pipe. So it's just a reminder that models are used to represent reality, but they are not reality. They are just a brief abstraction of it. And in this work, René Magritte was trying to play with us, and that's why he has this sentence. I think it's very appropriate for this case. So why should we model the urban water cycle? Well, first of all, to see how climate change is having an impact on cities. It allows us to design better sewer networks, better water distribution networks. It also allows us to design facilities to mitigate climate change, to mitigate flooding. It also helps us understand how different areas in a certain city are going to be affected by a given storm of a given return period. And on top of this, well, we can design strategies for minimizing the contamination of when a huge storm arrives. Sewers, depending on the conditions they were designed, will overflow and will contaminate the different waters. So we can evaluate how different strategies can help mitigate this contamination. So how can we model this system? So we're going to have some basic components. First of all, we need to define some initial conditions for our model and some boundary conditions. On top of this, we're going to discuss about three main disciplines, namely hydrology, hydraulics, and water quality. And we need to define the models and the parameters that describe these models for a given set of states on a period of time, for a time 0, a next time, until what we need to do to FAF the model. So let's look first at hydrological modeling. So we have different processes that involve temperature, atmosphere, rainfall, type of ground, storage, infiltration. So we have all these outside variables. And the simplest way where we model stuff in hydrology is by using what we can call buckets. So the different layers in a system can be represented by buckets that are connected somehow, and the flows of water between these buckets is described by simple equations or complex equations, depending on what we want to do. For hydraulic modeling, what we want to do is to understand how water flows in networks, how water flows in rivers, and model special elements in these networks, including tanks, including dividers, including pumps and weirs, and orifices. The main mathematical foundation for this modeling is based on the one-dimensional Sine-Venant equations, which are derived from the Navier-Stokes equations. A little bit more on this in a little while. So how do we model, how we arrange an hydraulic model? Well, first we need to define some nodes that represent manhole covers, pumps, tanks, or the boundary conditions of a system. On top of this, we have to define links, which can be pipes or natural rivers or different connections representing a pump, for instance. And each of these links contains a specific geometry and specific conditions, like roughness. On one side, we can have a pipe. On another side, we can have a natural occurring channel with varying geometry. Now, for the case of water quality modeling, we are interested in understanding how pollutants change over time, how pollutants disperse in water, how they degrade, how the concentration changes. So to do this, we basically use the one-dimensional advection dispersion equation, which is just saying how concentration changes over time in this case. And it has a couple of components. If we have, let's assume that we have a channel and a period of time A, we have a concentration of a given contaminant. What we want to do with this is understand how it propagates in the direction of the flow and how it disperses. That's why we see the blob growing and growing more dispersed. So now I wanted to do a little intermission on the Navier-Stokes equation, why it's important and why it's relevant recently due to some paper that was published last September. So in computational fluid dynamics, we have a very important equation that is called the Navier-Stokes equation by Claude-Louis Navier and Sir George Stokes. This equation, these equations, because it's a set of equations, you can see them on the right, is quite complex. They allow us to describe how viscous flows work, flow, and interact with each other. So for instance, with this equation, we can model the Kelvin-Helmholtz instability. On the bottom, you can see a model, a two-dimensional model of it. And on the top, you can see how this phenomenon occurs in nature when two layers of clouds are flowing in opposite directions. Why is this equation important? Well, the Clay Mathematical Institute has defined a set of problems. They are called the Millennium Problems. Among these, you can see the list there. There is a Navier-Stokes equations. And what's the problem? The question is, do solutions exist for this equation, and are they unique? So last September, a couple of researchers in Cambridge published this article, Non-Uniqueness of Weak Solutions to the Navier-Stokes Equations. So what does that mean? Well, it basically means that there are some problems with the equation. They found a situation where the solutions that are given by the equation are non-unique. So this, and in their words, it outputs nonsense. So this is normal because this is reiterating the thing that models are just a representation of reality, and the fact that the equation doesn't work under certain circumstances just means that we are not taking into account all the different things that we should be having into account. So now let's go back to the main presentation. And regarding how modeling works, and the US Environmental Protection Agency Department wanted to create some softwares to help understand the problems of sewers and water distributions. So they created, back in the 60s and in 1993, a couple of packages. One called SWMM, that is the one we're going to talk about today, that basically allows us to model the urban water problem for sewers and stormwater and infiltration, whereas EPA-NET is modeled for designing water distribution networks. The code for these programs originally was a mixture of Fortran and other languages, but it was rewritten in C around 2005. And with this rewrite, an interface was created, I think using Delphi, which is what you see on the right. So now going into the stormwater management model, it's a very sophisticated software, although the interface is not very modern. And the reference manuals that you can find to understand all the different components that we talk about, hydraulics, hydrology, and water quality, are quite thorough. And I encourage you, if you're interested in this topic, to read more about them. So when we are working with this model, what do we want to do? We want to, as programmers at least, we want to be able to create simulations easily. We want to be able to iterate on the different things that we are analyzing. But the problem was that SWMM, by 2007, didn't have an API to perform things programmatically, not even talking with a high-level language, like Python, for instance. So if you wanted to do something, and this is from the knowledge base, there was this doctor asking that one of the students want to perform some coupling of the SWMM engine, but unlike EPA-NET, there is no API. And at that moment, it was 2007, and until 2015, there was nothing done about it. So there was a huge problem there, and there was a gap that needed to be filled. Around 2 or 3 years ago, the EPA organization started publishing their software on GitHub, which allowed us to reach a broader community. Also, in the conference of PyCon 2017, Cathy Huff was talking a bit about the different tools that can be used to analyze the different problems that we're facing as humanity, and pointed out to a specific software, US EPA WNTR, Water Network Tool for Resilience, or how cities can learn to adapt to withstand the problems of climate change, rising temperatures, droughts, extreme rainfall events, among other things. So this is an invitation for all of you to go explore this site, because there are many pieces of software that are pretty interesting. Now, regarding the software, as I was saying, there are some limitations on it. Mainly, it only works on Windows so far. Until 2 or 3 years ago, there was no API to interact with the model. You had to go into C and code directly into it and bind directly into it, which is not very friendly. The GUI is showing its age. It's functional, but it's not the best. It doesn't allow to rapid prototyping or doing like quick work. And although there is a control language embedding into the software, it's not flexible enough for performing fast-paced iterations or hundreds of simulations that sometimes you need when you are trying to analyze, for instance, how probabilistic flooding can affect an area. So, just going to tell you a brief story of where I come from. On the left side, you see Acela Patriana. He was my mentor, my thesis advisor, when I was doing my master thesis in sanitary engineering. He also happened to be the first, or one of the first guys that was developing a binding, a Python binding for the SWMM engine, which are those 2 packages that are listed there in yellow. At that moment, for my thesis, I wanted to do a lot of things. I wanted to work with global climate models. I wanted to do downscaling, urban modeling, and I wanted to do all this with Python and all the other tools that were available. But downscaling is hard. So basically, I just stopped with one part of it. And although at that moment I did not use the tool, I did thought that it deserved a better name. So I went to PyPy and just registered a name, PySWM. Now back in 2006, Bryant, the guy on the left, contacted me and said, hey, I have this library that is doing this, and I wanted to upload it, and turns out you already have that name. Would you mind deleting it so that I can use it? So as any mature software developer working in open software, I say, no. And I just went on with it. And we just exchanged a few mails and did some stuff. And a couple of months later, we started working together. And now we have PySWM version 0.4.7. And since then, we have been working together, and we have been coding together. And that brings us to what OpenWaterAnalytics is. So the problem with the US EPA kind of like workflow is that even if they are on GitHub, they have limited resources. They are either working on SWM or they are working on EPA Net. And the way they work, because it's a federal agency and all the bureaucracy, it makes it hard to contribute to the code. So that's why in 2015, Bryant and Sam created OpenWaterAnalytics, which is basically a parallel organization that is working on the same software with the intervention of the people from EPA, but without the problems of bureaucracy and all the things that don't allow that the software progresses at the rate it should. There are also some people involved in the team. And a couple of days ago, we actually had a meeting, like the first official meeting with different guys from Mexico, USA, Canada, India, France, England. There is a huge team working now on this initiative. And the idea of moving to an open source system was like, this software was developed in the past by one or two guys working isolated with their own idiosyncrasy. No, how do you say that? Idiosyncrasy. And the problem also is that there are many research projects that are not participating in this development. And the move from these guys, they come from two companies, Mnet and CityLogic. So they're really pushing the use of these tools from the industry side. But we really want to get involved with the open source community. We really want to start working with academia. So this is my call to all of you to, if you're interested in these projects, you don't need to know about hydraulics, hydrology, or modeling per se. There are many things that you can do to participate. Documentation, you can learn about continuous integration, unit testing, C, C++, Python, many interesting things. So the SWMM API that was developed during the past 2 years is basically exposing the data model, which allows us to interact with this simulation in real time and perform more robust control than what we can do with the embedded language. So we basically have a computational engine. We have a toolkit API that was developed, and then we have Python bindings that are talking to this toolkit API. On one side, we also have an input API that processes all the geometry and data for running the models. On the other side, we have an output API that controls the binary output of the numerical calculations. At this moment, we only have the toolkit. We don't have a reliable binding to work with the input or output API. And currently, that's a problem that we aim to solve in this year. So we're working on it. So what does this PySWM binding allow us to do? Well, we can run simulations. We can change the properties of the conduits to simulate, for instance, how they get clocked over time. We can make control rules in Python instead of a weird language embedded. We can change how different inflows of water enter into the system at different stages of the simulation. So for instance, just to give you a brief example, we can use a context manager to start working on the simulation and iterate step by step, defined in a step to get a final report on a simulation. We can also adjust the link settings. This can be pipes, this can be rivers. so that we can query information on every time step, and at the same time we can change how the model works depending on rules. Like for instance, if at a certain point the flow is bigger than 10 meters per second, just change the orifice aperture or a gate to have only 50% of the opening available. And on top of that, working with Python, we can really express any type of custom control rules that we can do with the project. But at this point, the API is limited. There is no way to construct a model from scratch doing coding. So we have two choices. We have to either create the model using the GUI software, the graphical interface, or we have to create by hand or code it to create a file that looks kind of like this. And the problem with this file is that it doesn't make a lot of sense. You have this is just a small snippet of a file that has several hundreds of lines where the characteristics of conduits are defined in very different places. Because as the software has grew, the different facilities of it have been included in different portions of this, let's say, input file. So this poses a problem. It's not a very friendly format. It's not that easy to create. It's straightforward to understand. So the project right now is based on looking at a paper that was published a couple of years ago that created an object-oriented API net, the other software that we were talking about earlier. So the idea of this paper, of this project, was to create the whole model and simulation suite using Python and using object-oriented constructs. That way we can do something like this. This is not really something that is working currently, but it kind of gives you the idea where we would like to go with an object-oriented style of programming. We can create a model, then we can create a couple of time series, then we can create a rain gauge that represents how a storm affects a system. Then we can create the sections of different conduits. They can be circular pipes, they can be trapezoidal channels. And then we can create junctions with specific coordinates and elevations and then connect these conduits in a way that is very straightforward and allows to create, is very expressive and allows to create models very easily. So this is something we are aiming for, or at least I am particularly interested in this type of API. So why should we care about all these things, besides all the things that we can use to simulate? Well, we have a window to the model. Before this, it was a bit opaque. We could just put an input, run a process, and then get the output. Right now, we can really see what's going on every single step. We can create optimization routines so that we can focus on designing better networks based on minimizing cost, minimizing flooding. We can create new algorithms, and all of this we can do in Python, or at least that's the plan. We can watch the simulated results like in real time and affect them in real time. And any other thing that at this moment we haven't thought of yet is possible to work on this. So what is the roadmap and future work for this project and where I would like to invite you? Well, I talk about API Net and SWMM. These are very similar projects at their core. They're modeling nodes, they're modeling links, they have inputs, they have time series. So a big chunk of code could be shared between these projects, and at the moment it's not like that. API Net is also on the way from moving from C to C++, so it's already moving into an object-oriented paradigm. On the other hand, since this project is just recently starting to work in a more modern workflow of open source, we really need to work on unit tests, create conda packages, create continuous integration, and provide official cross-platform support. At the moment, we can run the simulation engine in Linux, Mac, and Windows, but this support is not official because we still haven't completely passed all the regression tests. So we could use a hand in this direction. On top of this, the idea is we should be able to create all these models on Python and interact directly with the model without having to go into C or going to C++. So the work to do this is still not there yet, but the idea is to modify this so that we can create our own custom infiltration models, our own custom quality models, custom optimization routines and rules, and try to run this all from Python. So we're not hiring. I work for this company. It's based in Bucaramanga. And my invitation is if you like C or continuous integration, C++, Swig, Python, bindings, hydrology, hydraulics, whatever of this, if there is any topic of this that interests you, just let's meet and let's talk. There is a lot of work to do, and I would be more than happy to get you on board with this project. So, thank you.